Lightning is often perceived as a sudden flash of light followed by thunder, a violent and chaotic event that appears to strike without warning. In reality, lightning is not chaos at all. It is the visible result of an orderly physical process governed by the same laws that control atoms, electricity, and particle interactions throughout the universe. To understand lightning, one must begin not in the sky but at the atomic level. Every atom consists of a positively charged nucleus made of protons and neutrons, surrounded by negatively charged electrons. Under normal conditions, the number of positive and negative charges is balanced, and matter remains electrically neutral. However, this balance can be disturbed. When materials rub against each other or collide, electrons can be transferred from one surface to another. This is why removing a synthetic sweater can produce small sparks and crackling sounds. These tiny discharges are not fundamentally different from lightning. They are lightning in miniature. Inside a thundercloud, this same principle operates on a massive scale. Powerful vertical air currents force water droplets, ice crystals, and partially frozen particles to collide repeatedly. These collisions cause electrons to be stripped from some particles and attached to others. Over time, a large-scale separation of charge forms within the cloud. Lighter ice crystals tend to become positively charged and are carried upward by rising air currents, while heavier frozen droplets become negatively charged and sink toward the bottom of the cloud. As a result, a thundercloud develops a distinct electrical structure. Its upper regions accumulate positive charge, while its base becomes strongly negative. This imbalance does not remain isolated. The negative charge at the base of the cloud repels electrons in the ground below, forcing positive charges to concentrate on the Earth's surface directly beneath the storm. The atmosphere between the cloud and the ground becomes an electrically stressed region, filled with tension that continues to increase as the storm develops. Lightning occurs when this tension becomes too great to be contained. Electricity always seeks the path of least resistance, flowing from regions of high potential to regions of lower potential. The greater the difference in electrical potential and the shorter the distance between opposite charges, the more likely a discharge becomes. This is why lightning tends to strike tall structures, mountain peaks, or sharp objects. These features reduce the gap that the electrical discharge must cross. Although lightning appears sudden, it is the inevitable conclusion of a process that has been building invisibly within the storm cloud. What follows is not a random act of nature, but a precise release of stored electrical energy, one that connects the microscopic world of electrons with the vast dynamics of the atmosphere. Before a lightning bolt becomes visible, the atmosphere inside and below a thundercloud is already in a highly unstable electrical state. The separation of charges within the cloud and between the cloud and the ground creates an enormous difference in electric potential. This potential difference is the true driving force behind lightning, but on its own, it is not enough. Air is normally an excellent electrical insulator. Even when the electric field becomes extremely strong, it should theoretically prevent a sudden discharge. This raises a fundamental question that puzzled scientists for decades. How does lightning manage to break through the insulating air? The answer appears to involve processes that originate far beyond Earth's atmosphere. High-energy cosmic rays constantly bombard the planet from space. These particles, originating from distant stars, supernovae, and other energetic cosmic events, travel at nearly the speed of light. When they enter the Earth's atmosphere, they collide with atoms of nitrogen and oxygen, knocking electrons free and creating cascades of secondary particles. This process ionizes the air, turning neutral atoms into charged particles. Ionized air behaves very differently from normal air. Its electrical resistance drops dramatically, making it easier for electric current to flow. Instead of a single straight path, cosmic rays create branching, irregular channels of ionization, similar to the unpredictable trajectories of billiard balls colliding on a table. These invisible ionized pathways act as temporary guides through which electrical discharges can propagate. Inside a thunderstorm, when the electric field grows strong enough, these ionized channels become critical. They provide the initial weak paths that allow electrical charge to begin moving downward from the cloud toward the ground. This early stage of lightning is known as the precursor or stepped leader. It advances in rapid, discrete jumps, each lasting only fractions of a millisecond, and is usually invisible to the human eye. Despite its subtlety, this precursor travels at extraordinary speeds, covering kilometers in a blink of time. As it approaches the ground, the electric field intensifies even further, drawing positively charged streamers upward from objects on the surface. When one of these upward streamers connects with the descending precursor, a complete conductive channel is formed. At that moment, the conditions for the main lightning discharge are finally met. What appears to us as a sudden flash is actually the final stage of a long and complex chain of microscopic and cosmic interactions. Lightning, therefore, is not merely a product of clouds and weather. It is a phenomenon shaped by processes that span from subatomic particles to interstellar space, revealing how deeply interconnected Earth's atmosphere is with the broader universe. Once the conductive channel between the cloud and the ground is established, the most dramatic phase of lightning begins. This phase is known as the main discharge, and it is responsible for the intense flash of light and the enormous energy release associated with a lightning strike. Unlike the precursor, which moves in small, fragmented steps, the main discharge travels as a powerful surge of electric current along the ionized path that has already been formed. Although it appears instantaneous to the human eye, this discharge propagates at several thousand kilometers per second, carrying a current that can exceed 100,000 amperes. The temperature inside the lightning channel rises to levels hotter than the surface of the sun, causing the surrounding air to expand explosively. This rapid expansion generates a shock wave that we perceive as thunder. The geometry of the lightning channel is far more complex than a single straight line. The main channel itself is only a few centimeters wide, but it is surrounded by a broader region of ionized air that can extend tens of centimeters outward. Within this region, energy is distributed unevenly, creating branching patterns and secondary discharges that contribute to the jagged appearance of lightning. Each strike transfers an enormous amount of energy in a very short time, measured in tens or hundreds of millions of volts and hundreds of kilowatt hours. On a global scale, thunderstorms collectively transfer trillions of kilowatt hours of electrical energy every day. Despite this immense power, lightning remains impractical as an energy source. The discharge occurs too rapidly and unpredictably, and the technical challenges involved in capturing and storing such concentrated energy far exceed current technological capabilities. Moreover, attempts to directly study or harness lightning have often proven dangerous, sometimes resulting in severe injuries or fatalities among researchers. Yet, even with modern instruments, many aspects of lightning remain poorly understood. Scientists can describe how energy moves through an established channel, but they still struggle to explain why lightning chooses one specific path over countless others, or why one ionized channel becomes dominant while others fade. This uncertainty highlights a fundamental truth about lightning. It is a natural phenomenon governed by physical laws, but it operates at the edge of our ability to observe and predict complex systems. Several environmental factors influence whether a lightning discharge will occur and where it will strike. One of the most important is the difference in electrical potential between charged regions. The greater this difference, the stronger the electric field and the higher the probability of a discharge. Distance also plays a critical role. The shorter the gap between oppositely charged regions, the easier it is for electricity to overcome the insulating properties of air. This is why lightning frequently targets tall structures, elevated terrain, and sharp or pointed objects. Such features effectively reduce the distance the electrical discharge must travel. Humidity further amplifies these effects. Moist air contains more water vapor, which facilitates the buildup and movement of electric charge. As humidity increases, the atmosphere becomes more conductive, lowering the threshold required for a discharge to occur. The shape of objects on the ground also matters. Sharp edges and narrow points concentrate electric fields more efficiently than flat surfaces. This concentration makes it more likely for upward-moving streamers to form from these locations, increasing the chance that they will connect with a descending lightning precursor. Altitude compounds all of these factors. Elevated locations not only shorten the distance to the charged cloud base, but also place objects in regions where electric fields are naturally stronger. Together, these conditions create a complex landscape of risk during thunderstorms. Lightning does not strike randomly, but follows the path that offers the least resistance under the prevailing atmospheric conditions. While this process obeys physical principles, its precise outcome remains difficult to predict because the atmosphere is constantly changing. Small variations in humidity, temperature, and particle distribution can significantly alter the electrical environment. As a result, two storms that appear nearly identical can produce very different lightning patterns. This sensitivity to initial conditions is one reason why lightning forecasting remains an ongoing scientific challenge. Understanding these factors is essential not only for scientific research, but also for practical safety, as it informs how buildings are designed, how lightning protection systems are implemented, and why certain locations are more vulnerable during storms than others. Despite decades of research, one of the most intriguing aspects of lightning remains unresolved: the exact moment and mechanism that triggers a discharge. Scientists can describe charge separation, electric fields, and ionized channels in detail, yet the final spark that initiates lightning is still not fully understood. This uncertainty exists because lightning forms at the intersection of many processes, occurring simultaneously and at vastly different scales. Microscopic particle interactions, turbulent air currents, atmospheric chemistry, and cosmic radiation all overlap in a narrow window of time and space. Even a small fluctuation in any of these factors can determine whether a lightning strike occurs or not. This sensitivity makes lightning an example of a system operating near a critical threshold, where minor changes produce dramatic outcomes. Another unresolved question concerns the precise path lightning follows. While electric current generally seeks the path of least resistance, the atmosphere offers countless competing routes. Ionized channels form and disappear rapidly, and only one becomes dominant enough to carry the full discharge. Why this particular channel wins remains unclear. Some theories suggest that subtle differences in ion density, temperature, or particle alignment give one path a temporary advantage that is quickly amplified. Others propose that stochastic or random processes play a larger role than previously assumed. These uncertainties are compounded by the extreme speed of lightning. The entire sequence, from initial charge buildup to final discharge, unfolds in milliseconds, making direct observation extremely difficult. High-speed cameras and specialized sensors have improved our understanding, but they still capture only fragments of the process. As a result, lightning research often relies on indirect measurements and statistical models rather than complete real-time observation. This incomplete picture has practical consequences. Without a full understanding of how lightning initiates and selects its path, it remains difficult to predict exactly where and when a strike will occur. Forecasts can identify conditions favorable to thunderstorms, but they cannot pinpoint individual lightning events with certainty. This limitation underscores the gap between our theoretical knowledge and the complex reality of natural systems. Lightning serves as a reminder that even familiar phenomena can harbor deep scientific mysteries, challenging assumptions about predictability and control in the natural world. The immense energy carried by lightning naturally leads to the question of whether it could ever be harnessed for practical use. At first glance, lightning appears to be an abundant and powerful energy source. A single strike can release hundreds of kilowatt-hours of energy, and across the planet, thunderstorms collectively transfer trillions of kilowatt-hours every day. However, this apparent abundance is misleading. Lightning releases its energy in an extremely short burst, lasting only fractions of a second. Capturing such a rapid and concentrated discharge without destroying the collecting equipment presents a major engineering challenge. In addition, lightning strikes are highly unpredictable in both time and location. Unlike conventional power sources, they cannot be scheduled, regulated, or directed reliably. Even in regions with frequent thunderstorms, the intervals between strikes and their precise impact points vary widely. These factors make large-scale energy harvesting impractical with current technology. Efforts to study lightning more closely have also carried significant risks. Researchers working near storms or using experimental equipment to trigger lightning have faced severe danger, and in some cases, fatal accidents have occurred. As a result, much of what we know about lightning comes from remote sensing, indirect measurements, and controlled laboratory simulations rather than direct interaction. These limitations further complicate attempts to fully understand and utilize lightning's energy. Despite these challenges, research into lightning continues because of its broader implications. Understanding lightning contributes to safer infrastructure design, improved storm protection systems, and better models of atmospheric electricity. It also provides insight into plasma physics and high-energy electrical processes that occur in other environments, including industrial systems and even astrophysical phenomena. Lightning, therefore, is less a resource to be exploited and more a natural laboratory, offering glimpses into extreme physical conditions that cannot easily be reproduced on Earth. Lightning stands as one of the most striking reminders of how much remains unknown about the natural world. Despite centuries of observation and decades of advanced scientific research, it continues to resist complete explanation. We understand its components, its scales of energy, and many of the conditions under which it forms, yet the precise moment of its birth and the exact path it chooses still elude prediction. This gap in understanding is not a failure of science, but a reflection of the complexity of nature itself. Lightning emerges from the interaction of countless variables, from microscopic particles to global atmospheric systems, and even influences originating beyond Earth. It demonstrates how local events can be shaped by processes occurring far outside their immediate environment. In this sense, lightning is not merely a weather phenomenon, but a bridge between Earth and the cosmos, linking atmospheric physics with cosmic radiation and subatomic interactions. Its immense power, compressed into fleeting instants, reminds us that energy does not need to be sustained to be transformative. Even brief events can reshape landscapes, ignite fires, and influence ecosystems. At the same time, lightning exposes the limits of human control. It cannot be tamed, scheduled, or fully exploited, only respected and studied. This reality challenges the assumption that every natural force must be mastered or converted into utility. Instead, lightning invites a different perspective, one that values understanding over domination. By studying lightning, scientists gain insights not only into storms, but into broader principles governing electrical systems, plasma behavior, and complex nonlinear processes. These insights ripple outward, informing fields far removed from meteorology. Ultimately, lightning serves as a symbol of nature's layered complexity. It appears simple at first glance, a flash and a sound. Yet beneath that simplicity lies a web of interactions spanning scales and disciplines. Recognizing this depth fosters humility and curiosity, reminding us that even the most familiar phenomena can conceal profound mysteries. In accepting what we do not yet know, we create space for discovery, and in observing lightning, we witness not just a discharge of energy, but a moment where the hidden structures of the universe briefly reveal themselves.